Hey, your turns. Welcome to exercise 20.7, where we take a look at solving trigonometric equations. So, firstly, we learnt about the unit circle and then how to graph a trigonometric function. And so, if we take a look at this graph here with the trigonometric function, where we've got the equation sine x degrees equals to 0.6. Well, in the function, what that would look like is 0.6 just halfway above between, or just above halfway between 0 and 1, all right, on the graph, and it's going to hit two places on the curve. And so that comes back to the ambiguous case we learnt way back in exercise 20.2. There's going to be usually two answers for sine and cosine. So working it out by graph is a little bit difficult because we don't have a machine drawn line, and so if we were to draw this line slightly wrong, okay, our crossing of the line on the x and y axes will be slightly different, and it's not going to get us an accurate answer. So to be able to solve trigonometric equations algebraically will give us exact answers. All right, because human error means we don't draw the line very straight and very accurately in this exact identical curve with grids. We need algebraic equations to prove our answer. So this is what we're going to learn today through the examples. Hopefully it'll make sense. And one of the biggest things you need to remember throughout year 11 and 12 is a summary of exact values. So when sine is 30 degrees, we're going to get an answer of half, or 0.5, meaning the height of that triangle inside the unit circle, I don't have a unit circle here, is going to be half. All right, when we're on a 45-degree angle, sine, the height will be 1 on root 2, which is the same as root 2 on 2 if we use our surds, where we multiply this equation here by root 2 on root 2. Okay, we'll get this answer like so. Sine 60 means we're going to have a height of root 3 on 2, which is something like 0.8666, so pretty close to 1. All right, so the bigger the angle, the taller and taller the height of the triangle becomes inside the unit circle. Okay, cosine talks about the length of the width in the triangle. All right, so when it's 30 degrees, we're going to have root 3 on 2, so on and so forth. And then tan, remember, is talking about outside of the circle. It's like sine's big brother in terms of the height of the tangent or the length of the tangent that's outside of the circle, which is like an extension of the height of the triangle, as we learned previously. So please do the previous exercises before you attempt to do exercise 20.7. Let's have an example, look at an example to try and make sense of everything. All right, this looks pretty complicated, but I promise you it's not. So the question asks us to solve the following equations. On the left, we have sine x in example A, and on the right of the equation, we have root 3 on 2. So this is where you need to go back to your table and go, sine root 3 on 2. Well, the mystery x is actually 60 degrees. So this x here is going to be 60 degrees. And if you're not sure, you can use a calculator to figure that out. The next part of this question is, comma, x is an element. So this e is just an element of 0 degrees to 360 degrees, meaning if we didn't have this domain restriction, we'd just go round and round and round and round and round because circles go on forever. It just means we want the x-axis of our graph to be 0 degrees and 360, meaning a full circle. Okay. In year 11 and 12, you'll learn what happens when we go a half circle and 2 circles and 3 circles. It just means we get more or less answers. All right, with a full circle, generally we get 2 answers. So here's a little cast rule. Some teachers will use this to teach this method. I think I will as well, but there's multiple ways to get to the answer solving this equation algebraically. So the first step is just check out what the trig function looks like. Okay, so on the left side of the equal sign, we zoom in a bit more. Let me just zoom in. That's zoomed in almost too far. Okay, so on the left side of the equation, the sine x, we can sketch. So we know sine, if we replace the x with 0, gets us 0. If we go sine brackets 90 degrees, okay, so sine brackets 90 equals 1. Sine brackets 180 equals 180, 0. That's not meant to draw at all. And then sine 270 is going to get us -1. Sine 360 is going to get us an answer of 0. So that's sort of our function and how we sketched it. On the right side of the equal sign, we have √3 on 2. So where that is it's actually, if you put √3 on 2 or √3 divided by 2 in your calculator, you're going to get an answer of 0.86666, an irrational number, and that's pretty close to 1. And so what we can do is we can actually go onto our graph and draw these dotted lines and see how many times it hits the graph. It hits the graph twice at approximately 60 degrees and 120 degrees. Now, this is pretty accurate because we have a gridded paper. Everything is well measured. Obviously, when you do it, you don't have the luxury of this. I'm just showing you the proof on the graph of how we sort of get our answer. So we're going to get two answers, 60 and 120 by the looks of it, because each little interval here is 30 degrees. So 0, 30, 60, 90, 120, 150, 180, so on and so forth. And then this is basically showing us what to look out for when we figure it out algebraically. All right, so let's try and do this algebraically. This is graphically. We don't want to do that necessarily. So the first step is 1. Okay, find our base solution. Okay, so our base solution is just using calculator. Rightio. So our base solution is just, if we think about it, let me just try and copy this in. So sine x √3 on 2. So therefore, if we use our linear equation skills, x is going to equal sine inverse √3 on 2. Okay, let's see what this is. √3 on 2. And this is going to get us 60 degrees. Okay, so our first answer is 60 degrees. And we know this already because 60 degrees is that point there. Okay, but we know there's two answers. And the annoying thing is we don't know what the other one is. But there's a way to go and find it out. Remember, sine and cosine, they're sort of like complementary, so supplementary. So if we go back to the ambiguous case with sine, what we do is the other angle. So number 2, find other angle. Okay, this is going to be a situation where we always go and take 180 minus 60. Now, why is it 180? Why is it 60? Well, if we go back to our cast rule, all right, what we have here is a positive √3 on 2. So it's saying sine x equals a positive √3 on 2. Which quadrants are sine positive? Well, we know quadrant 1 here is sine positive, and we got ourselves the answer of 60 degrees. So on our unit circle, okay, the 60 degrees looks something like, oh, that didn't work. 60 degrees looks something like this. That's not 60 degrees, is it? Okay, now we know sine is positive here because that's all ratios are positive. And in year 11 and 12, hopefully you learn the proof, but we probably don't have time for that right now. In quadrant 2, sine ratio is also positive. And to really try and draw a mirror of this triangle, we have to go always on the x-axis. So always x-axis. And here's going to be our other 60 degrees. And so we know this is 180 degrees. Okay, so to get to here where it's 60, well, we know this is going to be 120 degrees, which means the other angle is 120 degrees, like so. Okay, so our first angle is there in the unit circle, all right, from the right side of the horizontal. Okay, and our second side is 120, which is this line here. And that's why it's 120, because remember, we always travel this away, okay, with our unit circle. Now this is a mess. Okay, I wish we had a whiteboard, but that's sort of the case in the situation we're in. And if you go back to the graph, all right, hopefully you're starting to see the connection between the graph and the unit circle. All right, that point there is also 120 degrees. Okay, and this part here, 0.87, this just means the height of the triangle's line is going to be 0.86666, because when it gets to 1 here, that's the maximum height. So this height here is about 0.8666, so on and so forth. So hopefully that's making sense. There's another way to do it where we draw a line across the circle. Hopefully I can show you that at school some other time, but let's just learn this one method for now. All right, let's take a look at example B. Example B is a little bit more challenging because what you notice is here, they give us cosine 2x, okay, and the period's going to change, okay? There's no amplitude that's changing, but the period here has been essentially doubled, or actually, no, ignore that. It's been sped up. So the period has been sped up. I don't have a visual to show you, but I'll show you what that means when we get to the graph. On the right side, we have a negative. So we have a negative fraction of cos. So negative 1 on root 2. Okay, again, you have to go back to your summary of the exact values table. Cosine negative 1 on root 2, doesn't matter. Okay, it's going to be 45 degrees. Ignore positive, negative for this table. Okay, negative 1 on root 2 is also 45 degrees, because all 4 quadrants where it's 45 degrees will have the same sort of width. Again, do let me know if that confuses you. All right. This part in yellow, x is 0 to 360 degrees. This just means one full circle. And when we draw our function, we just go 0 to 360 on our x-axis. So the first step is let's just check out what cosine 2x looks like. So we sketch this trig function. And what we need to substitute is in our calculator, we want to type cosine brackets 2 times 0. That's going to still get us 1. The next part is we go, well, okay, let's figure out the next interval, 90. Cosine 2 times 90 is actually cosine 180. And we know cosine 180 is -1. And even if you didn't, if you put it into your calculator, cosine 2 times 90, all right, that's going to spit you out -1. If you go into your calculator again and go cosine 2 times 180, that's going to get you +1. Right, so it goes from 1, -1 to +1. Usually, if we didn't have this 2 here in front of the x, -1 would be at 180, and then this +1 would be at 360. But because it's been all squished this way, everything's been pushed this away, okay, because of the 2, we have a change in the period. Okay, so the period now is 180 degrees because after this 180 degrees, once we get to here, okay, it starts repeating itself. If you're not sure what I mean, if I were to draw in a text box to block this part out, All right, what you notice is we've got a V shape. And then if we were to go here, oh, look, it's the same V shape again. All right, but if we didn't have the 2, it'll just be one big V, okay, from 0 to 360. But because of the 2, we now have 2 sets of them in the space of 0 to 360 degrees. Now, in blue, the -1 on root 2, we have to think to ourselves, okay, well, let's see that as a decimal because irrational numbers sometimes, or in surds, it's hard to visualize if you're unfamiliar. That's about -0.1, sorry, -0.71 if you were to put in your calculator. So if you plug in -1 on root 2 in your calculator, -0.71. And if we were to draw a line from this point across with a ruler, hopefully nice and straight, we can see sort of the points of intersection. And there are 4 of them. So what this means is we're going to have 4 answers. Okay, so we're going to have, oh, that's not pointing to the right spot. We're going to have an answer here. Okay, so an answer here. We're going to have an answer here. We're going to have an answer here. And then we're going to have an answer here. So you can already see the answers we're going to get are below 1 below 90, 1 just above 90, 1 just below 270, 1 just above 270. So this means we're going to get 4 answers. And let's try and figure out these 4 answers algebraically, because again, you guys don't have the luxury of gridded paper and sketching it out and then trying to like draw accurate lines without, like, you can see my lines aren't very accurate. So it might not be exactly 60 degrees, whatever that degree point is. All right. These points, the point being, isn't accurate. That's why we need to solve it algebraically. So what we do is step 1 again of step 2 is to find base solution just by using our calculator. Okay, so cosine 2x cosine 2x equals -1 on root 2. Now, therefore, we know to get x by itself, we go 2x is going to equal cosine -1 on -1 on root 2, as we've done in the past over and over again. Do the calculations on the right side. So cosine -1, where we've got -1 on root 2. This is going to get us 135, but don't be fooled. This isn't quite our angle, okay, because we have a 2x. So if we were to get x by itself, 135 divided by 2 is going to equal 67.5. We'll just double check that. Yeah, 67.5. Woohoo. All right. So 67.5 is actually going to be our first answer. And as you can see, I drew it at 60. So this point is actually well off. That's why we can't trust the graph. We need to figure it out algebraically. So 67.5 is our first point. There's 3 others to find. And this is where we go and check out this fraction. So let me just write this down. So find other angles. Okay, by checking cast. You're probably wondering, what was cast? The cast acronym is that circle I attached above, and it's this point here, CAST. All right, we've got a negative cosine, and we want the quadrants where cosine is negative. All right, so previously we had a situation where sine was positive in quadrant 1 and quadrant 2. Okay, this time cosine is negative in quadrant 2 because only sine is positive in quadrant 2. So cosine is negative in quadrant 2. Cosine is also negative in quadrant 3. Okay, so this negative here, all right, links to this part down here. Whew, a lot of arrows. Hopefully you're making sense of that. So what does that mean? Well, we've already got ourselves 67.5. Let me just double check if that's correct. Yep, so 67.5. And you're probably wondering, well, Ed, 67.5 isn't in a quadrant where cosine is positive. That's because this 67.5 was a situation where we halved 135 degrees. So 135 degrees was in a negative cosine quadrant, but because we halved it, it goes into a non-cosine negative quadrant, which is fine. Okay, but how do we get the solution to our next answer? Well, if we think about it, what is negative 1 on root 2? If we check our exact values, negative 1 on root 2, or just 1 on root 2, is 45 degrees. Okay, and we know cosine is negative in quadrant 3 as well. So the 135, this 135 was already covered off, okay, in quadrant 2. So the next answer must be in quadrant 3 before we halve it. Okay, so once we halve it, it's going to be in another different quadrant, and that's fine. So 45 degrees, okay, quadrant 3, we always add or subtract from this middle line. Okay, the middle line here is our x, and this point here is 180, which is going to be the closest, which means it's going to be 180 degrees, okay, plus 45 degrees. Okay, where did we get this 45 degrees? Once again, this 45 degrees was grabbed from the summary of exact values here. Okay, all right, cosine 1 on root 2, 45 degrees. How did we get the 180? Well, we knew that the first base answer was 135 degrees, which was in this quadrant 2. The next answer must be in quadrant 3 before we halve it. And so this part here is, let's see, 180 plus 45 is 225. Let's try and make this a bit clearer. So should say 2x equals 180 plus 45. So therefore, 2x equals 225. And then our second point is going to be at, well, 225 divided by 2, which is 112.5 degrees. And so what that means is if if you think about it, all right, we're going to have another situation where we've got 67.5, 112.5 degrees if we were to go this way. Okay. Or if you think about a 180 takeaway, 67.5 is going to get us this same answer. All right, but we know there's 4 answers. We know there's 4 answers. How do we find the other 4 answers where we have a situation where this and this is also going to be 67.5 degrees? So not to scale. How do we get another one of these sort of situations? Well, what we do is we add the period. So step 3 of, I guess, solving it algebraically. Okay, find remaining angles by adding period. Okay, so the period, okay, is 180 degrees, okay, because that's when it starts repeating itself, as we can see in the graph. Oh, we figured out our second answer. Let's go and highlight that as well. So that's this part here. In the unit circle, that's there. On the unit circle, the first one is like there, super messy, I know. I'm just trying to link everything together. And so the next 2 answers we see, it's just an exact replica of this part. Okay, so if we just add 180 to this and 180 to this, we'll get this answer and this answer respectively. So 67. Okay, so therefore 67.5 plus 180 is going to get us to 147.5 degrees. Where is that on the graph? That would be like, so that's 270. It'll be like somewhere there. Okay. That will be that one there. Okay. And then the very last one would be 112. This all looks too messy. So 112.5 plus 180. Guess that's 292.5 degrees. Okay, and then that means this one here. And what you notice is each one will have like a situation where we've got 67.5, 67.5. Apologies for the lack of neatness. Okay, from there to there. And notice how it's always touching the x-axis. All right, so it's one of the key pointers. And that will be the 4th answer. All right. Where did we get these ones from? Just from the answers above. So there's 67.5. That's meant to have a point there. In yellow, 112.5. And then the period is obviously what happens once we sketch the graph. So make sure you follow the steps closely. Might have been a lot to digest. So do ask if you have any questions. But that's it from my end. I might just change the highlighting of these colors here so we don't get it confused. So let's go and use pink. Okay, so that part's there in pink. That part there is also in pink, okay, based on the negative. And because we divided by 2, it shifted out of the quadrant 2 and 3, which is fine. And eventually we got ourselves the answer. And so I'll just write these in just in case. So this is 67.5 degrees. This here is 247.5 degrees, and then this here is 292.5 degrees. Okay, so that's sort of the situation here. Just make sure we fence that off. Alrighty, long one. Hopefully it makes sense. Super complicated, but I'm sure you're up to it. Thanks, everyone.